So today we're going to be continuing looking at linear systems of ODEs. And in order to do that, we need to also talk about some things called complex numbers. Now, before the pre-lecture, before you watch that, I hope you guys have watched that. Who had heard of complex numbers before? Okay, not many of you. Okay. So, and there's been a little bit of time just talking a bit about complex numbers and why they matter in this context, just to make sure those are clear, before discussing parts of the pre-lecture. I'm not going to go through too much about specific and general solutions. These aren't going to be a big component of the course. Most of the questions I'm going to be asking you in relation to things like systems of ODEs are going to be understanding what's the long-term behavior, calculating eigenvalues, and drawing phase planes. Okay, so I'm not going to be asking you typically for like an exam question to find what is the specific solution, what is the general solution, things like that. Okay, so let's start off talking a little bit about complex numbers. So essentially, up until now, everything that you've met as a number exists on the real number line. Okay, so this is a one-dimensional line like this: 0, 1, 3/2, a little bit further on, pi, somewhere over here, -1, -5.5, and so on. Every single number that you've met exists on this line. Now, when we have complex numbers, what we're essentially doing is we're extending this line now to think about a plane. Okay, so this is now the complex plane, where we have this vertical axis here corresponds to the imaginary part of this number, and the horizontal real line still exists, so that's the real part. So we have a real part and an imaginary part to our complex numbers. What does this imaginary component actually mean? Well, we represent it by a lowercase I, and we define that to be equal to the square root of -1. Now, usually we can't take the square root of negative numbers, okay? But if we define I to be the square root of -1, then we can take the square root of any number, whether it's positive or negative, and the negative ones, the square root of them will have this factor of I in them. Okay, so that means that when we have a complex number, so for example, here this Z is equal to A plus IB, we have A as being the real part, so whatever exists along this real line, and the B being the imaginary part. Now, B itself is a real number. I is the imaginary number, okay? So for example, here, this just gives us a coordinate in this complex plane. Up here, say this is A, B, and our complex number would be Z is equal to A plus IB, or BI, doesn't matter. Okay, so this is an extension of the real numbers. Why do we care about this? Well, when we try to solve a quadratic equation, what we're really doing is if we've got a quadratic equation like ax squared plus bx plus c is equal to 0, if we try to plot this, we might end up in a situation like this, where this curve crosses the axis twice. So we have two real distinct roots, so two values of x that solve this equation. Okay, when you plug this into your quadratic formula or you factor it, that's what you end up getting. Okay, that's one possible outcome. We might also get something like this. If we shift this up, I'm going to shift it over a little bit as well. We might get something like this where we just touch that x-axis. Okay, so when we just touch that x-axis, there's only one real root in that case. For the blue one, there are two real roots. Those two real roots were distinct. Okay, so two solutions to our quadratic. What happens if we shift this up further? Now, in this orange case, we don't intersect the x-axis at all. Okay, so this means that we have 0 real roots. But if we define this I to be equal to the square root of -1, we end up with two complex roots. So by defining these complex numbers, what it means is that we can solve any quadratic equation, even if it doesn't intersect the x-axis. Okay, so that's why we're interested in them. What does this have to do with linear systems? Well, if I jump later into the pre-lecture material, when we are trying to find eigenvalues for our matrix, and the eigenvalues tell us about the long-term behavior of the system, we end up finding the characteristic equation. So for a 2x2 matrix, this gives us a quadratic equation, which we must then solve. What happens if we end up with something under here, under the square root, it's a negative number? So remember, this could define some real biological system. There's no reason why we can't end up with a negative number under here. So we need to figure out what's going to happen. The complex numbers tell us something specific about the type of dynamics that we get in the long term. Okay, so I'll come back to that in a moment. The key thing here to remember about complex numbers, they have a real part, they have an imaginary part, and they represent points in a plane known as the complex plane. Okay, so let's tie this all together then, thinking about linear systems. So we talked about linear systems of differential equations the other day, where we can write them in this form here. The dx1 dt, dx2 dt, the x1 and x2 are our two variables. We have these equations being linear in x1 and x2. So we have these coefficients a subscript I and j here, which means that we can write them in matrix form. Okay. I'm going to gloss over the specific general solutions. Like I said, this is really for background information to understand where things come from, but I'm not going to be asking you to solve these things in an exam. What really matters here is that when we end up with our general solution, we have our eigenvalues, our lambda1 and lambda2 for our linear matrix, in this case, our linear system. These appear in our solution. So because we've got e to the lambda 1t and e to the lambda 2t, the value of lambda 1 and lambda 2 is going to determine whether our solution grows or shrinks. Okay, so assuming here that lambda 1 and lambda 2 are both real numbers. Okay, so here they're distinct real numbers as well. We're not going to do cases where lambda 1 is equal to lambda 2 because that's a little bit more complicated. So essentially, they tell you about the long-term behavior of the system, just like when we did our population models before. Finding our eigenvalues told you about the long-term behavior. So when you hear long-term, think about eigenvalues. I talked a little bit the other day briefly about when we're drawing phase planes, what our eigendirections mean. So we can draw null lines, and on those null lines, we can think about whether we're crossing left or right or up or down. But our eigendirections tell us something slightly different. In this case here, these are our null lines. So that's when our dx1 dt and dx2 dt are equal to 0, respectively. If we draw on our eigendirection, so this is if we find an eigenvector and then just draw a straight line through that eigenvector, starting at the origin. Here we've got these eigendirections here. What you see on a phase plane is that everything gets pulled in the direction of your eigenvectors. So these eigendirections are, again, telling you something about what's happening in the long term, and the arrows on those eigendirections tell you whether something's growing or shrinking, okay? So if they're pointing towards the origin, then everything is going to get shrunk towards the origin. If they're pointing away, then they're going to get pulled away. In this case here, we've actually got a saddle because some of the arrows are pointing towards the origin and some are pointing away from the origin. And whichever one turns out to be the biggest, in this case, it's always the thing that points away, that's going to eventually dominate the system, and everything is going to get pulled in the direction of the arrows that point away from the origin. Okay, so we can think about null lines, we can think about eigendirections. In general, I'm going to focus on getting you to think about finding eigenvalues when we're looking for algebraic solutions, and drawing null lines and direction fields when we're doing graphical solutions. So there's nothing to stop you doing eigendirections if you would prefer to do that, but I'm going to focus on null lines for that aspect and eigenvalues for the algebraic aspect. Okay. Okay, so we talked a moment ago about this solution here, and we have our lambda 1 and lambda 2. If our lambdas are less than 0, then this e to the lambda t that appears in this general solution is going to shrink towards 0. And if it's greater than 0, then it's going to tend towards infinity. So this is, again, a little bit of a contrast to our discrete time models, where we cared about whether our eigenvalue is greater than 1 or less than 1. That was because in those cases, we had a lambda to the t in our solutions. So if lambda is less than 1, then this is going to shrink towards 0. And if lambda is greater than 1, it's going to grow. Now we've got, in our continuous time models, we've got e to the lambda t. So in this case here, the key value is whether we are less than 1 or greater than 1. Whereas when we have e to the lambda t, we care about whether our eigenvalues are positive or negative. Okay, so it's shifted where we need to think about checking the values of those lambdas. Okay. So what does this mean? If both of our eigenvalues in these cases are negative, then we get a stable node. So everything tends towards our origin. If one of them is positive, one of them is negative, we have a saddle. So you move towards the origin in one direction, but you're pulled away from it in the other. And if they're both positive, then we have an unstable node. We can see this again from the solution here. If both of these lambdas up here are negative, then e to the minus something times by t is going to tend towards 0 as t gets very big. If it's positive, then it's going to grow. If one is positive and one is negative, in the long term, you're only going to care about the one that's positive. Okay, because the e to the minus something times by t is going to tend to 0, and e to the positive something times by t is going to get very big. Okay. So complex eigenvalues, what do they actually mean? So this has all been real eigenvalues up to this point. It turns out that we don't have to solve this this quadratic equation every time. If we've got a matrix here, A is equal to A, B, C, and D, so these are our coefficients that come from our linear system, we can calculate something called the trace and the determinant. So we know the determinant already. If our trace is just the sum of these values on the main diagonal, okay? So we usually call this tau. This is the trace of our matrix A. So that's A plus D in this case. This delta we usually refer to as our determinant. In this case, it would be AD minus BC. So we already know how to calculate the determinant, but the trace is the new thing here. And we can also calculate this thing that's highlighted in green. This is called the discriminant. You don't need to remember that it's called the discriminant. But this bit here will tell us whether our eigenvalues are real or whether they're complex. Okay, so if tau squared minus 4 delta, so if we take our trace and we square it and then subtract 4 times the determinant, if that's positive, then we have real eigenvalues. If it's negative, then we have complex eigenvalues. What do these complex eigenvalues mean? Well, it turns out that when we write our solution for complex eigenvalues, we end up with these trigonometric terms in them. And what do trigonometric terms, cos and sine, do? They oscillate. Okay, so complex eigenvalues means oscillations. So in the context of our models, those oscillations are going to be spirals or things called centers. Okay, so either you just keep going around your origin in an orbit, or you circle in, you spiral in, or you spiral out. And whether you spiral in or spiral out depends on the sign of the trace. So this tau here, which is from our matrix up here, if we add this A plus D, if that's negative, then our spirals, our oscillations are going to decay in amplitude. So we're going to tend towards the origin in the long term. If they're positive, then we're going to move away. They're unstable. And if it's equal to 0, then we just move around in ellipses. Okay. One final thing on this. If we work out that we've got some sort of oscillations in our system, we don't know the direction of those oscillations, and that might matter. Okay, so for example, if we're talking about like a predator-prey system, you often see oscillations in predator and population sizes, and those you typically see something like the prey population size will increase, and then the predator population size will increase, and then the prey population size decreases, and because there's no prey around, the predator population size decreases. We'll talk about this when we come to our nonlinear systems, but sometimes the direction of these oscillations can matter, okay? So how do we work out the directions? Well, if we know in this case here, for this example, there is a spiral and it's stable, we don't know whether we're spiraling in like this, going this way, or if we're spiraling in the other way. What we do in this case is we can think about the direction field at some point. So for example, on one of our axes, in this case, in this example here, I've just chosen this vertical axis. So when x1 is equal to 0, we substitute this in, and then that gives us the direction of these arrows here. Therefore, we know the direction that we're crossing those axes, and hence what direction we're spiraling in or out. Okay, last thing, this here, which I will include on the formula sheet in the midterms, it tells us based on the value of our trace and the value of our determinant. So we've got our trace going in this way and our determinant going in this way. And then we've also got this curve here, this parabola, which is tau squared minus 4 delta, sorry, tau squared is equal to 4 delta in this case. So above this, we have tau squared is tau squared is less than 4 delta. So we have complex eigenvalues. Below it, we have real eigenvalues. So this diagram here tells us, based on our trace and determinant and our tau squared minus 4 delta, where we are and what type of dynamics we have. So whether we have stable or unstable spirals, whether we have saddles, and whether we have stable or unstable nodes. Okay, that's quite a lengthy introduction. The reason I've gone through a longer introduction today is because there's quite a lot of new material in that in terms of complex numbers in order to make sure those are clear. It may take a little bit of time to get used to the idea of extending the real line into complex numbers. But I also have office hours today, so feel free to come and ask me about that afterwards as well. Before we go on to any problems, does anyone have any questions about the pre-lecture material? No? Okay. Okay, so this first problem, I'm going to leave to the end if we have time, or I'll leave it as an exercise for you guys. Essentially, what we have to do here is we're given a solution to what's called an initial value problem. So an initial value problem, we have a system of ODEs here, and we have an initial value. So a point where you're starting at. What are your initial conditions? What's your initial value of x1 and x2? We want to verify that this is indeed a solution to this. So how do we do that? Well, to verify that this initial condition is satisfied by this solution here, we just need to substitute in t is equal to 0 and check that we get this vector. And then to check that it satisfies the dynamics, well, we need to think about the left-hand side and the right-hand side of this equation down here. So to find the left-hand side, we just differentiate this solution here. So we've got x of t, some function. We take its derivative, and we'll get some vector. On the right-hand side, we have this matrix times by our solution x. Okay, so we take this solution x, plug it in here, take our matrix, multiply it by that solution. Again, we'll get a vector. And if it is indeed the solution, these two things will match. Okay, so whenever you're asked to verify that something is a solution, essentially you need to make the left-hand side balance the right-hand side. So work out the left-hand side, work out the right-hand side, and check that those two things match. Okay, so that's how you solve that. I'll leave that as an exercise because I want to focus a little bit more on our graphical representations as well as using our trace and determinant. Okay, so we're given 3 matrices here, and we're told that these are matrices for linear systems. So we've got dx dt is equal to a, each of these matrix times by x. What I want you to do in these cases is classify the origin. So in these linear systems, we only have one equilibrium, which is our origin. I want to work out whether that origin is stable or unstable, and whether it is a spiral, a center, a node, or a saddle. Okay, so essentially find out where you are on this diagram using these matrices. Okay, so I'll go through the first one with you guys. So we don't have to work out our characteristic equation. We can actually just rely on our trace and our determinant. So our trace in this case is going to be the sum of these elements on the main diagonal. So we have 2 plus minus 1. So this is 1, which is obviously positive. So that tells me immediately, because the trace is positive, I'm somewhere over here. I'm in one of these possible scenarios, okay? Now let's think about our determinant. So here we take 2 times by minus 1 minus 0 times by 0. This is minus 2, and so this is negative. So if we go back to our diagram here, our determinant is negative. So that means I'm down here. So the only possible, I don't even need to worry about tau squared minus 4 delta in this case, because I know at this point I have a saddle. So this tells me the origin is a saddle. And let's do one more together. So we've got this new matrix here. What is our trace? Give me -2, -4. So that's -6. That's negative. So if we go to our diagram, we have a negative trace so that we know we're over this side here. Now let's work out our determinant. So we have -2 times by -4 minus 1 times by 2. We're going to have 8 minus 2, which is 6. That's positive. Again, let's go back to our diagram here. The determinant is positive, so I know that I'm in this upper left quadrant here. I don't know whether I've got a stable spiral or a stable node. So I have to now look at the sign of tau squared minus 4 delta, okay? Because that's going to tell me which side of this red curve that I'm on. So take the trace, square it, -4 times the determinant. A trace was -6, so square that, we get 36. My determinant was 6. So if I take away 4 times by 6, 4 times by 6 is 24. This is 12. So this is positive. Remember, this tau squared minus 4 delta comes from the solution to my characteristic equation, where we ended up with a square root of tau squared minus 4 delta in my solution to the quadratic. Okay. So since tau squared minus 4 delta is positive, that means this is positive, so we're taking the square root of a positive number. So we have real eigenvalues. We have 2 real eigenvalues. Now, to get oscillations, we need 2 complex eigenvalues. So what this tells me is I'm below this curve here. I have a stable node. So 0, 0 is a stable node. Okay. A little bit difficult to do because being able to see everything. Have a go at doing this last one here, and I'll go around and answer any questions. Okay, let's see how you guys got on. Okay, so we've got this matrix here, 0, 1, -1, 0. So what is our trace? Our trace is just going to be 0 plus 0 equal to 0. So this is a borderline case, and borderline cases are problematic biologically for a number of reasons. But we've got our trace is equal to 0, which means that we're sat on this axis here. This is a slight aside, but like this is a problem in biological models when we end up with a situation like this one. We're on a borderline here, or say we're on this borderline here between 2 types of outcomes, or this borderline here, which you refer to these models as being structurally unstable, because in the real world, any slight variation, there's a bit of randomness in the population, or, a bit of additional complexity that we've not captured, it pushes us either into this case or into this case, or here between these cases, or over here between these cases. So they're structurally unstable in the sense that you are sitting on a knife edge between 2 possible outcomes, and any sort of environmental variation you would have would push you one way or the other. So they're kind of unrealistic, but mathematically they're possible. So what do we have here then? So we've got our trace is equal to 0, so we know that we're sat on this yellow line here. Our determinant is going to be 0 times by 0 minus -1 times by 1. So 1, because this is positive. So that means we're actually on this part of the line here. In this case, we have a center. So centers are just where we're on the borderline between a stable and an unstable spiral. So you're neither spiraling in or spiraling out, which can only mean that you're just going around in an ellipse. Okay, they're drawn as circles here, but they don't have to be circles. They could be ellipses like this. They could have these strange kind of, well, that arrow should not be going that way. They could be going like this. They could be something like this. Okay, they're drawn as circles here, but they don't have to be circles. Okay, so being able to take our linear systems and look at our trace and our determinant is really important for telling us what goes on in the long term. We don't necessarily have to plot our phase planes. We don't necessarily have to actually calculate our eigenvalues. All we're doing here is our conditions are telling us whether we've got real eigenvalues, whether we've got complex eigenvalues, and what the sign of the real parts of those eigenvalues are. Okay, so these are really nice, simple conditions that we can use. I had one question about what happens if tau squared is equal to 4 delta. So in this case, if we've got tau squared equal to 4 delta, we sit on this curve here. So this is one of those borderline cases, which we're not going to cover in this course. In this case here, what it means is that we have one real eigenvalue that's repeated. Okay, so this is when we have a case like lambda minus 4 squared is equal to 0. Okay, so the roots to this, we just have one root that's repeated twice. Okay, that is a little bit more complicated. We're not going to cover that because it is one of these structurally unstable cases. What other questions do I have? Someone asked about whether we can ever have one complex eigenvalue. The answer is no. If we have complex eigenvalues, they always appear in pairs. So if you have lambda 1 is equal to a plus bi, lambda 2 is equal to a minus bi. Okay, they always appear in these pairs. These are known as complex conjugate pairs, where the imaginary part has a different sign. Okay, any questions about this stuff before we move on? Incidentally, when it comes to linear, non-linear systems, we'll be doing exactly the same sorts of analysis, but we'll have more than one equilibrium, and it won't necessarily be at the origin. But the same principles hold of looking at our trace and our determinant will help us figure out what goes on in the long run. Okay, let's talk a little bit about eigendirections. So here, we're asked to sketch a phase plane for this system of differential equations. We don't know what our matrix A is, but we're given our eigenvalues and the corresponding eigenvectors of our matrix A. So we don't know what this looks like, but we can, we don't know what matrix A looks like, but we can deduce what goes on just by looking at our eigenvalues and eigenvectors. Okay, so what do we have here? We've got lambda 1 is minus 1, so it's negative. Likewise, lambda 2 is negative. So we know that in our solution, we've got e to the minus something, sorry, e to the minus 1 times by t plus something with an e to the minus 2t. And this is going to tend towards 0 as t tend towards infinity. Okay, so we know that eventually we're going to tend towards our origin. So this means it's going to be stable. All of our arrows are going to be pointing towards the origin. Let's think about what this axis looks like. So I'm going to plot an x1 and an x2. Okay, how can we draw this phase plane? Well, we have our eigenvectors, v1 and v2. So this v1 here, if we started at the origin, we know that we're moving 1 unit up and 1 unit to the right. So this is my v1. Okay. Because our eigenvectors, if you remember from earlier in the course, they're unique only up to non-zero scalar multiplication. So I can multiply this by any non-zero scalar and I've still got an eigenvector. That's what it means for it to be an eigenvector. So what that means is that all of my eigenvectors sit along this line here. Now, this was V1, my eigenvector that's associated with my first eigenvalue, lambda1. And because this lambda1 is negative, we know if we start on any point on this eigendirection, any point on this line, we're going to be moving eventually towards the origin. So my arrows on this eigendirection point towards the origin. That's because for this part here, it's e to the minus lambda 1t, so e to the minus t is going to decay to 0. And let's think about our second eigendirection. So here we're moving 1 unit to the left and 1 unit up. So my second eigendirection, my eigenvector, sorry, is my v2. Just like the other one, we can draw a line, a straight line that goes through this, roughly. This and this is going to be my second eigendirection. And just as in the first case, we think about the direction we would move in if we're sat on that line. Because we've got this e to the minus 2t, our eigenvalue is negative here, minus 2. That means that if we sit on there, we decay towards the origin. So notice the difference when we're plotting things with eigendirections and with null lines. If we're on an eigendirection, if we're on this one of these straight lines here, our arrows are moving parallel, they're moving along that eigendirection, okay? Why is that the case? We've got a dx dt. Dx dt is equal to a times by x. Remember, if x is an eigendirection, or sorry, if x is an eigenvector, so we think of x as being this v1, we're just going to have lambda times by v1, lambda 1 times by v1, okay? That's what it means for it to be an eigenvalue and an eigenvector pair. Okay, so that just means we're scaling that eigenvector. We're either making it bigger or smaller, or potentially changing its direction. But in this case, because lambda 1 is negative, we're going to be shrinking it, okay? So we're going to be moving towards the origin. If it was positive, then the arrows would be pointing away. So when we're doing eigendirections, these arrows point along our eigendirections. When we have null lines, remember we did these the other day, if you've got a null line like this, and say a null line like this, in this case, on those null lines, one of your variables has either dx1 dt is equal to 0 or dx2 dt is equal to 0. So on those null lines, you're moving, say, left or right, or up and down. Okay, so the difference between null lines and eigendirections, note the direction of your arrows changes. Okay, so if you're doing eigendirections, the arrows go along, whether they're going in or out, and whether you're doing null lines, they are crossing those null lines. Okay. Okay, so the question actually asks us to plot some solution trajectories. So what do we know? Well, suppose we start off somewhere over here. This is my initial condition. I know that I'm going to get pulled in towards the origin. Okay. We actually know that V1 is going to be dominant. So because lambda 1 is -1 and lambda 2 is -2, eventually this second part here of our solution is going to get very small relative to the first part, okay? So that means that we're going to be tending towards our eigenvector. It's given by V1, okay? So this eigendirection given by V1, we're going to be pulled towards that. So that's why we go like this rather than going like this. That's a slightly subtle point, but it helps us to figure out what's going on. So if we start down here, we get dominated by the top, the eigendirections going from bottom left to top right. So you get pulled in like this. Likewise here, if we start here, we'll get pulled in this way, pulled in this way. Note, unlike our null lines, our trajectories are never going to cross our eigendirections. So when we're doing null lines, we would see things like this. We cross our null lines. When we're doing our eigendirections, our trajectories don't cross. They get pulled in those directions, but they get pulled in parallel to them eventually in the long term. In this case, pulled in towards the origin. Whereas when we did our null lines, we cross our null lines. Okay. For the last few minutes, have a go at doing the same thing as I've just done here, but for this second case. Okay, so you've got your eigenvalues here, one of them positive, one of them negative, and their corresponding eigendirections. So have a go at plotting that case. I'll leave this up. Hope you guys can see that well enough. Just to give you some hints as to what to do. Okay, it's just a few minutes left, so let's finish this up. Just to clarify, when I was going through this example here, this stuff on the right-hand side doesn't correspond at all to this system here. This was just illustrating if we have null lines, then our direction arrows cross those null lines, whereas on our eigen directions, we go along the null along our eigen directions. Too many terminologies here. So this stuff in green does not correspond at all to this system here. It's just an illustration as to what the contrast is between eigen directions and null lines. Okay, so let's quickly draw out this system here. So just like before, always make sure you label your axes. This is something that some students do. And another thing as well, when it comes to exams and IQs, if you're drawing phase planes, please draw them big. Often see something like this, like you guys are rationing paper, especially when it's digital, and we see these tiny little diagrams here. Please don't ration paper, especially when it's digital. Okay, so what do we have here? We have these two eigen directions. So V1 is 3, 2. So that means we're going 3 units to the right and 2 units up. So it will look something like this. So if I draw that as an eigen direction, it will go something like that. The other one, we're moving 4 units to the left and 1 unit down. Oh, sorry, 1 unit up. So 4 units to the left and 1 unit up is something like this. So if I draw my eigen direction going through that, it will look something like that. So this is my V1, this is my V2. What about our arrows? Well, on V1, because lambda 1 is positive, we move away from the origin. Lambda 2 is negative, so we move towards the origin. So if I draw some trajectories, suppose I start over here, I'm going to move towards the origin, but then eventually get pulled away like this. Here, again, I move towards the origin, but then pulled away here. So you see that my V1 is dominant, because we always eventually get pulled in the direction of V1. Can anyone tell me what this is, or all together? That all, thank you. Okay. That is the end for today. I have office hours now. Have a great weekend.